What's up guys, welcome back, or if you're new here, the end game for this project is repowering a BMW i8 with a Mazda 13B turbo rotary engine, and we're going to keep the factory hybrid system intact because, let's face it, it's going to be nice to have that extra torque as well as an alternate source of motion when we have a rapid unscheduled disassembly. Today we're going to talk about some of what goes into building custom electronics because it is a nice skill to have in your back pocket, as sometimes when you're working with off-the-shelf controllers, they might come up a little bit short on what you're trying to achieve. I didn't happen to go to school for any of this stuff, I just had a problem to solve and then jumped down the very deep rabbit hole. Today we have a new problem to solve, which is about 6 months ago I bought a Zestek OEM hub, which, truth be told, is actually a very nice piece of hardware that allows you to mount a 6-bolt aftermarket race style steering wheel and still retain all of the multifunction steering wheel buttons for your audio and cruise control, all that stuff. Now, to be very clear, Zestek does not list the BMW i8 as a compatible vehicle, and if you had a normal F-Series or G-Series or A90 Supra, this should work just fine in your application. I assume that because under the skin the i8 is mostly an F-Series BMW with a carbon fiber chassis and doors that make it difficult to park in tight spaces, that this would work, but that was incorrect. As you saw from the intro, that resulted in a cruise control malfunction, and looking up the code, it was a LIN bus error for some incorrect data transfer. If you're not familiar with LIN bus, it is a single wire automotive communication protocol that is most commonly used with things like power window switches, HVAC controls, and in our case, the multifunction steering wheel buttons. The guys at Zestek were actually really accommodating and wanted to work with me to come up with a solution, but we both came to the conclusion that their CAN bus version was going to be much better suited to my build, offering me more flexibility, and I had the skill set to be able to make the interface board to the car. So as we move from the OEM hub to the CAN hub, we can compare some of the physical differences. The OEM hub, not surprisingly, has a couple more switches as well as a couple different switches. Notably the ones on the side, which are rotary encoders, infinite turn with a push button, and then the buttons on the bottom are a joystick style, which are also rotary encoders with a push button. The CAN version omits the side rotary encoders and then goes to a discrete position encoder, which these are going to be for our boost control and our traction control settings. We also have a shift light. The 13B is going to rev a lot higher than the OEM setup. So rather than looking at the tach, we're going to be able to rely on the LEDs for where we are in the rev range. Both of these use the same magnetic flappy paddles and offer a very satisfying click. So issues aside on my setup, this is actually a very nice setup if you just want to plug and play deal to interface with all your OEM functionality with your cruise control, audio controls, all that stuff. Before we dive into designing an interface PCB, we first need to do a little reverse engineering of the factory system and understand what we're dealing with. The best place to start with a BMW is the factory diagnostic software of ISTA Plus. We type in the device that we want to investigate. We go to SSP for the wiring diagram. And here we can see that we just have very few wires. We have a power, we have a LIN bus, we have a ground, and then we have an output for, or rather an input for the horn and our flappy paddles. Next, we can click on the interface to give an idea of where the actual connectors are. We can also get some additional information about how this thing functions. The notable point here is that it uses a resistance-based setup to know which gear shift paddle is being depressed. So we do need to actually physically connect to the car and the LIN bus to start logging the data to see what we got to do with it. This is actually a unit that Zestek had sent on loan during some of our troubleshooting. I actually got to send that back to him shortly after I finish this video. The other thing you'll see here are some pre-terminated DuPont connector kits. These things come from like Amazon or AliExpress. They come with a connector housing that you can trim to whatever length you want, and it's compatible with both the male and female pins. The reason that that is convenient and nice to have is that many of the BMW connectors use the same 2.54 millimeter pitch between the pins. The pitch is the spacing between the pins. And so we can have a quick little breakout harness to plug right into the factory setup without having to cut in any wires. This one right here is only for logging the wheel as a standalone. I did have a breakout harness that was essentially a Y harness, but I have since taken that one apart to use for other purposes. Now that we have a general overview of how the system works, I did a little data logging of the factory LIN bus signals to see what the data stream looks like, because there's no sense in designing a PCB if we're going to have an unmanageable amount of data that we're going to have to recreate. One of the best ways to identify the data coming out of the device you're trying to reverse engineer is to simply unplug it and then see which messages are no longer present. So let's bring up 2 data logs and see what that looks like. So we'll take a quick look at what the data from the car looks like, and we have 2 different logs here. The first of which is the stock fully functional car, and then the one on the right is a log of the car starting out fully functional and then unplugging the steering wheel about halfway through. One of the best starting places to understand what messages your device is sending is to simply unplug it. Over here you can see that the master device is issuing a request, and these 2 IDs are not giving a result, which gives an event of slave no response. And so what we're going to want to do is see if there's any other missing devices on the bus in stock form, but we only have the IDs 02 and 04. So if we do the same over here, we have 01. So what that tells us is that 01 is going to be the data payload for all of the button statuses on our steering wheel. So we've quickly identified the main data payload, and we also want to look for anything that is inconsistent with the data pattern. If we scroll through here, we'll notice that everything comes through in a pretty consistent pattern. However, at the start of the wake up, you'll notice that there is some additional requests here. And if we look at the LIN bus standard, OX3C and OX3D are some diagnostic IDs, so those are probably interesting. Let's take a look at those. So we have something of interest that we uncovered. The way that this appears to work is that the master will send an ID request to the slave. The slave will respond with a data payload that corresponds to the request. If we look over at the unplugged log, the master is sending its ID request. There is no response, so it sends another request and another and another, and you can see that these are all different. It looks like it is cycling through various known device IDs trying to find the one that's installed on the car. So in addition to our OX01, we're going to have to deal with issuing a response to these requests. Because it's just 2 message requests that appear to be consistent throughout, we only need to worry about sending 2 signals that match these. So that's all we're going to touch on the actual LIN bus data in this one. We will cover the programming aspect on a part 2 video. So from our previous data log, since we already figured out what message we need to send for the wheel to issue a response for button status, we're just going to send some LIN messages. As you can see, I've already been doing some sending, but we only care about sending a OX01 message, which is going to elicit the response. We're just going to loop that, hit list send, and now you can see we have a nice clean data stream. And then what you're going to do is sequentially make a list of all the buttons and then go through and then hold them down one at a time. Then we can log the changes. See, this one is changing on byte number 2. Likewise, if we move over here, byte number 3 is changing. And so we just systematically go through all those, and then we'll have a log of what the car is going to want to see to remain in its happy state. Now, one thing you can see at the very beginning of the log, we don't immediately get a response. That is likely because the wheel is in a sleep mode, and once it starts receiving the messages, it'll wake up and then sending a response. Okay, so the last bit of probing that we're going to need to do is for the switches. And all of them do connect to ground. First, we'll just confirm the horn. As expected, that's just a quick momentary contact. We go to 0 ohm, so it's a dead short to ground to trigger the horn. And then the slightly more interesting one is the paddle shifters. which from the ISTA documentation says that is a resistor array basically. And so we've got about 3.2K of resistance at idle. And if we actuate the left paddle, that gives us a reading of 328 ohms. If we actuate the right paddle, that gives us about 1K ohms. So basically the way this works is there's going to be 3 resistors in parallel, the 3.2K, the 1K, the 330. The actual values of the parallel resistors are going to be a bit different, but for the sake of our discussion, we'll just keep it simple. So the body domain controller is going to see the changes in resistance. It's actually going to read that as a change in voltage, and then that's going to tell it which paddle is being pressed. So between the 2 analog circuits and the LIN bus, we have all the information that we need to go and design our adapter PCB. The software that I use for electronics design is, depending on who you ask, called KiCad or Kicad. I am on team KiCad, so we're going to call it that from here on out. And it's a pretty fully featured software that allows you to create schematics, PCBs, 3D viewers. Probably the best software that I've found that will get you what you need without paying a boatload of money for a more professional tool like Altium. And if you're not doing anything like advanced bill of material management, RF designs, things like that, then this is going to do more than enough for your needs. This is completely free and open source, and it is available for any major operating system. So I think the best way to approach this is to look at a finished design and then work backwards from there. When you open the software, you have a couple different working environments. The schematic editor and the PCB editor are the main areas that we're going to focus on. If we open up the schematic, this is basically where you're going to start, and it is essentially a component level wiring diagram. In order to make it a little bit more readable and digestible, I usually break it up into sections, with each component having all of its grouped supporting pieces together. We can start with the microcontroller. We have our switched outputs, which are going to handle our horn and our resistor array for the flappy paddles. We have some CAN bus circuitry. This is going to communicate to the CAN bus and do our 2.5 volt differential 2-wire output. This is our LIN circuit, which is going to have our 12 volt logic LIN bus. We have a debug port. This is how we're going to connect our programmer to the STM32. We've got a simple linear regulator power supply. And then we've got our connectors defined, as well as our airbag resistors. So you might be asking yourself, how do I go about choosing these components? First, you're typically going to start with a microcontroller and then add any of the additional functionality that you might need. The best way to do that is to find a working example or development board and then copy their layout into your project. In this case, we have an adapter PCB that is 100% functional in your standard F-Series or Supra. So we can look at some of the design stuff. Here we have an STM32 microcontroller. We have a CAN bus transceiver, which is going to talk to the steering wheel via the CAN. We have a LIN bus transceiver, which is going to generate the correct LIN bus signals. And then we have a power supply, which is going to take our 12 volts down to 5 volts, and then another power regulator that's going to take our 5 volts down to 3.3 volts, because most of the ICs that you're going to be using for communication in your microcontrollers, those all typically run on 3.3 volts these days. If we flip over to the back side, we've got another connector, and then here we've got some switching transistors, which are going to handle all the switching for the flappy paddles and the horn button. Typically when you get a component, if you open up the data sheet, it will give you what the appropriate layout's going to be. It will give you typically the recommended values for the capacitors or resistors, all in support of that. So you can see we have a number of capacitors with different values to handle any of the voltage stabilization. And then same thing elsewhere. We've got every single power pin has a capacitor. There's some pull-up resistors for the boot pins on the microcontroller. And then on the CAN bus, we've got our 120 ohm terminating resistor that I usually put a solder jumper to enable it or disable it. And then there's a 10K pull-down resistor. All of this is called out in the data sheet. So you don't need to have any electrical engineering degree to figure this out. You are just literally reading the manual. All in, this is actually a really basic circuit and probably representative of something that you might create, where you have your controller, you have your connectivity, you have your power, and then you've got some switched outputs. And that's probably going to cover most of what you're going to do in the hobbyist automotive space. At some point, you might end up adding some analog inputs for sensors if you want to do that, or some high current, high side switching drivers to drive high current power. So you can create a circuit with maybe 2 or 3 switch channels rather than having to spend like $1,500 on a PDM, and that's a good use case for this type of design. So after you are done with the schematic layout, you're going to move to the PCB layout. And again, this might be a little overwhelming to look at if you're seeing it for the first time. However, the 3D view might be a little bit less threatening. If you're used to looking at CAD, this is maybe a little bit more digestible. And you can see all the final layout of the components. And when you go to do your layouts, typically you want to group like components together. So over here, we have all of the passive components for our CAN bus. We've got our LIN bus over here, obviously our microcontroller. We have transistors for our switched outputs. We have a power supply, and actually we have 2 high side switches that aren't going to be in the board that we show you now. This is actually an update that I did after receiving the first boards, because I want to have a little bit more controllability for something that we'll get into. So jumping back to the layout screen, the first thing that I am going to recommend you do is to always create a 4-layer board. The cost over that of a 2-layer board is pretty much inconsequential. It allows you to create a solid fill ground plane in the middle, and then a solid power plane in the middle as well. And that is going to simplify your routing tremendously, because if we take a look at this capacitor that's on the power pins of our microcontroller, we end up with 2 very short traces, and then we sync to the planes by some vias. Vias are basically plated holes that are drilled through the PCB and allow you to interconnect layers from either side or any of the inner layers. If we pull up the power plane, you can see that it creates voids around the vias where we don't want to connect. And likewise, that switches back to the power on the ground plane. So not only is this going to make your life significantly easier from a layout perspective, it's also going to be a more reliable board with less electrical interference. If you have power and ground traces running all over the place, all willy-nilly, you're basically creating a bunch of large loops and antennas that can potentially create havoc with the rest of your signals. The other tip that I would have is whenever you're routing something that might be carrying any current, like your power, as they say, copper is free. When you have a PCB made, you can have all 4 layers completely solid copper and it won't change the price. So you really lose nothing by having nice fat traces or large ground pores or power pores to connect everything together and have a greater current carrying capacity so you don't generate a bunch of heat. Since we started with the completed layout, let's remove all of the traces to see what that looks like. All of these white lines are called a rat's nest. They are all linked to the schematic and going to define all the connections you have to make. So it's really just a long, tedious process of playing connect the dots. For example, here we'll click the wire tool, and then we select our via. Now the white rat's nest line disappears and we've got our completed connection, and then we just got to go through and repeat it for all of these. Now this is fairly simple because all of the components are already laid out because we're just stepping backwards from a completed board. So let's clear the board and then see what it would look like if you started this from scratch. So this is what you're presented with. So usually what I will do is hide the rat's nest from view and then just start arranging these things in a reasonable manner. You'll notice that there is no board outline here. So you can do something by either creating a simple edge cut layer with a shape. And you can see in 3D view that is now representative of the edge cut that you installed. Alternatively, you can import a DXF file of the PCB as an edge cut. So you design this in Fusion and then export the DXF, import it into Kicad, and then you have your custom shape. So bouncing back to our completed design, the one thing that you always want to make sure that you have no errors on is the design rule checker. We'll run the DRC. It shouldn't give us any errors. There are some warnings because I imported this project from Kicad 6 into the newer Kicad 8. So if we look at the warnings, they're just some notes about footprints, misalignments between the libraries, but we have no errors. Just for example, if we create an error, it will point you in the direction of where the problem is. So if we just go and fix that, run our check again, and everything's fine. So in order to get this made, you need to send files to a PCB fabrication house. In my case, I've been using JLC PCB for the last 5 years or so. If you're going to use their services as well, then I highly, highly recommend the Fabrication Toolkit plugin. JLC requires their fabrication files, particularly in the bill of material and the position files for the pick and place machine, to be in a specific format, and this will take care of all the file generation in one click. So if we're ready to go, we just click generate. That gives you a zipped folder of the Gerber files. That gives us a pick and place position file as well as our bill of material. Now that we have all those files, let's head on over to JLC PCB's website and see how to get these things ordered. We are simply going to add our Gerber file, in which case we're going to want to click the zip file. Once it processes all of the files, it's going to give you a visual representation and then update all the pricing according to your selections. Everything looks like it did in Kicad. We are at a whopping $7 for a quantity of 5 PCBs, with shipping about 18 bucks. You can go through and change your solder mask color. I prefer black. That bumps our price up to about 15 bucks. You can also choose other colors like purple, red, blue, whatever. In our case, we want to get these fully assembled, so we're going to click PCB assembly, only assemble on the top side. We are going to confirm parts placement, click next, get another visual confirmation of the side that you want to be assembled, click next again. We'll add our bill of material file, it's our BOM. We add our position file, which is our CPL file. Then it confirms all of your component selections. In the schematic, if you noticed any of the purple numbers that began with a C, these are the JLC PCB part numbers. If you populate that in your schematic, everything will transfer over to the bill of material and everything will automatically confirm, which is pretty convenient. Hit next. 3D file will render the positions of the components. You can confirm that. Usually when you upload the file, some positions will be off. They might be rotated a bit. Don't worry about that. Just click through and there will be a human that goes through and repositions everything based on the pin 1 marker on the silk screen of your PCB. So this is the final pricing. It is just shy of 150 bucks for 5 PCB assemblies. So if you create a device that might be useful to others, you can sell the remaining 4 at a nominal fee and recover your costs pretty quickly. Typically turnaround time is about a week. The PCB fabrication time is 3 days, and then assembly is another 2 to 3, and then shipping from China via DHL to me is usually another 3 to 4 days. Now, it wouldn't really be on theme with this project to just bring the steering wheel back to its original state of functionality. One of the other things that I needed to do with this build was to integrate an LCD screen somewhere in the car in order to display some sensor data, drive modes, things like that that aren't present in the factory display. I originally wanted to do something like a gauge pod on the dash somewhere, but I didn't really love any of the ideas that I'd come up with to date. I was also planning on doing the design of the display, but I am perfectly happy and content to design and program hardware that involves communication, switched outputs, reading sensors, things of that nature. But if I'm able to buy a screen that also happens to be CAN enabled, then sign me up. There happens to be a German company called CANChecked who makes some really slick displays that integrate into the OEM dashes of popular European performance cars, As you might expect, the BMW i8 is not a popular platform, so they do not make something for my vehicle. However, they do make a universal display called the MFD32, which is a 3.2-inch LCD screen that is CAN enabled. They also have a universal MFD28, and I'm sure you could figure out what the size of that screen is. I decided to integrate that screen into the steering wheel assembly, so I had all of my buttons and switches as well as the data right at my fingertips, and I also didn't have to mess with the flowing lines of the dashboard. So let's take a quick look how I went from a CANCheck's universal design to a housing that integrates with the steering wheel. This likely would not be an episode of Couchbuilt without at least some Fusion 360 and some 3D scanning. So we conveniently have a step file of the CANChecked MFD32 screen, which was an extreme time saver of not having to model that myself. And here we have a 3D scan done with my new Shining 3D Einstar Vega in HD mode. This took all of a couple minutes to scan and got reasonable resolution for us to design our housing from. So we're going to start by bringing in our CANChecked model. I've already removed the top cover plate. The CANChecked bottom plate is still present, and we use that to get our minimum spacing from the steering wheel. So let's get rid of that. And you can see that it doesn't leave us a whole lot of space to work with, but that is okay. So I basically took the position of the CANChecked model to make a cutout in which I need to support various places on their assembly. Then I made a housing that, as tightly as I could, hugged the curvature of the steering wheel. And for assembly purposes, the 6 bolts that mount to the hub are going to mount through the housing base, and that's going to hold everything together. Then we just mount the rest of the assembly on top of that. So we'll bring in the rest of our model there. You can see from the section analysis how that all goes together. We got some clearance on the back side. You might notice on the CANChecked housing that there is a cutout for a USB cable. I omitted that, so that does mean we're going to have to remove the top plate to access the screen. But once it's set up, we shouldn't be having to go in there very often, so not a big deal. I would much prefer the cleaner long-term look without any additional gaps or holes in the assembly. So our main components fit in there. We have the actual display itself. You can see that everything is pretty well centered. There is some dead portion on the screen over here that is not actually any functional pixels, so the actual viewing area is indeed centered. And then we simply add our top cover with a little embossed embellishment. This is going to get 3D printed in SLS nylon for high temperature durability, as well as a nice surface finish. And I think the final product cost all of a whopping $20 to our friends over at CraftCloud. So that's it for the design of how we're going to mount the CANChecked screen to the steering wheel. And I think our PCBs should be arriving just about now. So let's take a look how those turned out. Our PCBs have arrived, but we do need to add a couple connectors on the back side. And one of the connectors was actually not in stock when I ordered these. I most often use a chisel tip for the soldering iron. I'm going to tin our mounting pads. Position the connector, apply heat, wait for it to drop down, indicating the solder is melted. Repeat on the other side. Whenever you're doing SMT assembly, flux is your friend. It's going to help the solder flow onto the pads and not the solder mask. We simply drag solder across, and then we're ready to go. These are panelized by JLC PCB to assist in the SMT assembly, so these just snap right off. And then the first thing you're going to want to do on any new board is check the resistance between your power and ground pins. It will indicate whether you have a direct short anywhere. You should either have a very high resistance or no connection at all. Now that we've got our PCBs, let's do the final assembly, test this thing out on the car, and see if our problem is solved.
I did remove the Molex connector on the back of the CANChecked unit, replaced it with some lead wires to gain a little bit more clearance. I also needed to make a custom 8-lead harness for the Zestek hub, as the supplied harness only has 6 connections. In order to make use of our new 8-pin harness, we needed to solder the leads to the back side of the interconnect. And now we need to drill into our nice carbon fiber faceplate to allow pass through the connector. There are a choice of decals that will indicate which position the rotary encoder is turned to.
All right, let's see if our situation has been resolved. Power up. We've got no cruise control malfunction, but it is cold outside. We're in manual. We've got flappy paddles. We've got a horn. The smaller wheel really makes a huge difference in the feel of the steering. It does obscure the turn signal indicators, but we're driving a BMW, so that doesn't really matter. It also does obscure the check engine light, which is also an added benefit because we are driving a BMW. So I think what we will call this a win, and in another video we will have to move on to the programming aspect, getting our CAN bus hooked up. Now I do have some additional work to do in connecting the CAN bus, some more programming, and like I said, we'll cover that in a part 2 video, but that's the general overview and process of creating a custom electronic device for your project. And I'm not going to pretend this is for everybody, but if you have the ability to install a standalone ECU on, say, an engine that's not very popular, purely by following the manual, reading the factory wiring diagrams, understanding and choosing sensors, reading the crank trigger scope, all of those basic things, then you have enough baseline knowledge to make the jump to designing some electronics of your own. As I said earlier, I didn't go to school for any of this stuff. I was self-taught by a lot of the resources that are available, especially on YouTube, and I will link to some of the YouTube channels and websites that I found beneficial in the description, so definitely check those out if you want to learn more. If you do decide to start making your own electronics, be prepared to fail at the start. You're definitely going to make some mistakes, some of which you can fix with some bodge wires, like this example, which was my very first PCB, and you can probably smell this through the camera, but as bad as this dumpster fire looks, which is also why I have dumpster fire graphics on almost all of my PCBs now, it actually worked. After having some jumper wires and fixing some connections. This actually lived in the car for about a year and did everything that I needed it to. And if you take your hacked fix, put it in a nice sealed automotive enclosure, it'll be your little secret. If you made it this far, thanks for watching, really appreciate it. This video was actually a bit of a challenge to make because it covered so much ground in a short time, and I wanted to keep it at a level that was reasonably easy to follow if you're not going to be doing this stuff yourself, but also give you enough insights to start getting started on your own if you do want to pursue that path. Part 2 isn't going to immediately follow, but the next video is going to cover some of the things that I've been working on concurrently that haven't justified their own standalone video, but are definitely worth checking out. So we'll see you next time.